Alright, so in this video we're going to take a look at mechanical energy, and so the energy associated with an object that's in motion and is raised at different heights. And we're also going to link that into power, which is essentially the rate of exchange of energy. So let's start off looking at some definitions of the different principles that I'm going to be using. So first off, kinetic energy, are often abbreviated to KE for simplicity. It's the energy associated with the motion of an object. So if an object is not stationary, so it's travelling at a certain speed, it has a certain amount of energy associated with that motion. So it's half times the mass times the speed squared. Energy is a scalar, so you don't need velocity, you just need speed or the magnitude for that one. Gravitational potential energy, often abbreviated to GPE. This is the energy associated with the height of an object. So we usually do things with reference to the ground. So we say the ground is zero potential energy essentially. Once we get to A2 we'll change that model a bit, but at AS that works for now. So essentially, the higher an object is, the more gravitational potential energy it has, and that varies linearly. So the GPE is the mass times the gravitational acceleration, or the gravitational field strength, 9.81, times the height of the object in meters above the ground. So I'm going to be talking about mechanical energy. So mechanical energy is just the sum of the GPE and the kinetic energy at a given moment in time. So if you add them together, that gives you the total mechanical energy the object has. And the final thing I might talk about in this video is work done. So that's the energy transferred by a force, and forces act to change the mechanical energy of an object. So if you apply a force, you can either increase or decrease the mechanical energy the object has by transferring it to other forms. And you can calculate the work done by knowing the magnitude of the force and the displacement in the direction of that force. So S is the symbol for displacement. Okay, so those are our definitions. So let's have a look at the principle of conservation of energy. So in the previous video we looked at conservation of momentum, so the total momentum of a system has to be conserved unless you're getting some external force from somewhere. It's exactly the same with energy, so the total energy of a system stays the same unless you get some extra energy from somewhere else. So an external force comes in, you're heating something like that could introduce some more energy to the system, but if you're not doing that, the total mechanical energy stays the same. And as a more general rule, the total energy of a system is always conserved. So if we look at, I don't know, like the universe or whatever, we don't ever have any more additional energy. We've always had the same amount. And then the part that you'll have learned about even from year 7 science, I think this is in, we know that we can't create or destroy energy, it can only ever be transferred from one form to another. So a falling object transfers GPE into kinetic energy because it's accelerating. And when we look at resistive forces, you might do some work against their resistance as well. Okay, so let's look in a little bit more depth at kinetic energy. So as I said before, kinetic energy is a scalar. All forms of energy, in fact, are scalars. Energy, the direction does not matter at all. And the other thing is that if you don't do any work against external forces, so you don't increase the height above ground level or do any work against resistance, kinetic energy won't change, which means the speed won't change, which is essentially stating Newton's first law. So unless any forces act to change the kinetic energy, it will stay the same. So let's have a look at an example of using kinetic energy. So 500 kilogram car, pretty typical mass of a small car, traveling at 20 meters per second and accelerates to 30 meters per second. Calculate the change in kinetic energy. So first of all, if we want to calculate the change in kinetic energy, I'll usually abbreviate that to delta KE. That's going to be the final kinetic energy minus the initial kinetic energy. We always define a change as final minus initial. So that's going to be half m final speed minus half m initial speed. No, I've just used m in both because the mass hasn't changed at any point. So we can factorize this. So we can take the half m out of both expressions to simplify. And we get Vf so there should be a squared, Vf squared minus Vi squared. As a side note, it is definitely not half m Vf minus Vi all squared. It's not that. I've seen that a lot of students do this. That's if you multiply out that bracket, those two expressions are not the same. So be careful. We want the expression I've got in red here. So let's put some numbers in. So we've got 500 divided by 2, 30 squared, which is 900, minus 20 squared, which is 400. So that ends up being 500 if I'm not mistaken. So 30 squared, 900, minus 20 squared, gives you 500 times 500 divided by 2. We've got two significant figure numbers, so we should express this number as two significant figures. So 1.5 times 10 to the 1, 2, 3, 4, 5. 10 to the 5 joules, because it's a unit of energy. So that's the change in energy of the system during that acceleration. Okay. So that's kinetic energy. So before we look at GPO, we have to take a look at work done. So work done is the product of the force, so whatever force you apply, and the displacement in the direction of that force. So if they're in the same direction, so force and displacement in the same direction, that's just W equals Fs. There's an angle between the force and the displacement, so just to give you an example. So you might be applying a force in that direction, but it's actually travelling in this direction. So that you think quite a lot of sailing examples you have, like the difference between the force of the wind and the displacement, for example. You get stuff like this with an angle theta in between them, and you'd calculate the work done in this case as the force times by the displacement in the direction of the force. So you actually find the component of the displacement in the direction of the force there. Okay, so let's have an example of putting that to practice. A 20 kilogram object has a velocity of 20 meters per second. It's acted on by a force over a distance of 10 meters, but the force is at 10 degrees to the displacement. So let's first of all draw some kind of diagram. So we know it's 20, and let's say it's going in at 20 meters per second, and we know it's going to travel that way a distance of 10 meters, but we know it's acted on by a force of let's say, well, for simplicity, let's go 10 newtons. I probably should have specified in the question, and it's at an angle of 10 degrees. So you have it like that. And what we want to do is calculate the new kinetic energy of the object. So the first thing is to calculate the change in the kinetic energy, which is going to be equal to the work done, because any work you put in is going to be to increase the kinetic energy. We know that the F theta, so it's going to be 10 times 10 times cosine of 10. Make sure your calculator is in degrees for this. Cosine of 10 times 10 times 10, which is 98.4. Yeah. If we work out the initial kinetic energy, we know that's half mv squared, which is half times 20 times 20 squared. That's going to be a lot of 20s. Okay, so that's 20 times 20 times 20 divided by 2, which is 4,000 joules. That's joules as well. The final kinetic energy is going to be the initial kinetic energy plus the change in kinetic energy, essentially adding those two numbers together. So it's 4,000 plus the previous part, which is 4,098, or it's going to be, what, 4.1 times 10 to the 3 joules, once we give that to two significant figures, like the information in the question is. Okay, so that's how we can link kinetic energy and work done. So putting in work can increase the kinetic energy, or working against the motion can decrease the kinetic energy. All of this was assuming there was no height change. Alright, so that's those. So let's finally look at gravitational potential energy. So this is actually the work you're doing against gravitational forces. So the force of gravity is the weight force, which we know is mg, and the displacement in the direction of the force is the change in the height of the object. So actually the gravitational energy is the force mg times the displacement h, so it's mgh. So you can calculate the gravitational potential energy by doing mgh, or the change in gravitational potential energy is mg delta h. So an object falls from a height of 30 meters to 10 meters. Calculate the velocity of the object, assuming that it was initially stationary and there's no work done against resistive forces. So let's summarize the information we've got. We know that the work done is 0, and we know the initial velocity, which we usually give the symbol u, is 0 meters per second. So first, let's calculate the change in gravitational potential energy. Remember, it's GPE final minus GPE initial. I'm going to factorize straight away because I showed you that earlier. So it's going to be mg times by 20. You'll notice the question doesn't actually give you what the mass is, but you'll see in a second that we don't need it, and that's minus because it's 10 minus 30, so we get minus 20. Now, if we lose gravitational potential energy, that must be transferred to kinetic energy. So we must gain kinetic energy. So the signs should be opposite, which means the change in kinetic energy would be the opposite sign. So it's 20 mg. So it's not minus 20 mg. We know the initial velocity is 0, so we can actually say that half final velocity squared, I would have a subtract the initial, but it's 0, is equal to 20 mg. And then, so you can see here, this is why we didn't need mass, because the mass is going to cancel out in these two equations. So we get the final velocity is going to be taking the half across, so 40g square rooted. So that's square root 40 times 9.81. Square root of answer is 19.8, so it's going to be 20 meters per second, to two significant figures there. So just to quickly recap what I've done there, I think we've got the change in gravitational potential energy, so it ends at this is 10, and it started at 30, so that's why we get this minus sign, minus 20, and then no energy is lost, so we know that if it loses this much GPE, it must gain this much GPE. We know the initial velocity is 0, which is why I would have it here, but I left it out. Mass is cancelled, we rearranged to give us the final velocity there. Okay, so that's our three different types of energy. So now let's link those to power. Okay, so power is defined as the work done per second, or the energy transferred per second. So therefore it would have the units of joules per second. However, we gave it a special name as a science community, and we named it after James Watt, who did a lot of fantastic research into like thermodynamics, electricity, those kind of things. So it's given the symbol W and called a watt, and that's the unit of power. So you'll come across two types of power, average power and instantaneous power. So average power is you're usually given some energy change and the time at which that energy change happened. You're not necessarily given an indication of when in that period the energy transfer was, but from that you can calculate the average power, so change in energy over change in time. So let's give an example of that. So we've got a 500 kilogram car accelerating from 5 to 10 meters per second over 10 seconds. Calculate the average power. So the first thing is to calculate the change in energy, which in this case is kinetic energy, because we haven't talked about any others. So that's going to be the final kinetic energy minus the initial. Like this. So it's going to be half times 500 times by 10 squared minus 5 squared, which is equal to, what's that, 100 minus 25 times 500 divided by 2, just 18,750 joules. And now we know the average power is the change in energy over the time over which it occurred. So it's this 18,750 over 10 seconds. So just take off the 0. So that's 1875 to 2 significant figures. That's going to be 1.9 times 10 to the 3. And it's a watt. That's average power. The other form, as I said earlier, is called instantaneous power. So essentially that measures how much force or something like an engine can give when it's travelling at spinning at a certain velocity. And so this is what you deal with when you're dealing with like cars and those kind of things. If you're given brake horsepower, what it's essentially telling you is how much force it can give at different velocities. So you actually calculate instantaneous power by multiplying the force and the velocity. So let's give you an example. So we've got a car travelling against a resistive force of 2,000 newtons, and the engine can produce 200 kilowatts of power. Calculate the maximum speed. So the key to this question is actually realising at maximum speed, acceleration is 0, because if it wasn't, then it would keep increasing its speed. So if we think of this car, we know it's acting, we've got a 2,000 Newton resistive force acting against it. And if it's not accelerating, that means the engine is producing 2,000 newtons. That's why it's not accelerating. The resultant force is 0. So what we've got here is the force produced by the engine. So we know that power is the force times velocity. We're trying to get velocity, so power divided by force. So it's going to be 200, it's kilowatts, so times 10 to the 3. And we're going to divide that by 2,000, which gives you 200 times 10 to the 3 divided by 2,000, which gives you 100 meters per second. How fast is that? So let's calculate that miles per hour in something you might be more familiar with. So 100 meters per second. So first let's convert it to meters per hour. So times by 60 to meters per minute, times by 60 again. So that's meters per hour. And there's 1,600 approximately meters in a mile. So divide by 1,600 gives you 225 miles per hour, which is probably a more familiar car unit of speed that you come across, which is pretty damn quick. Not many cars can do that. This must be a very high performance car, or a very low air resistance in this case. But typically you would give answers in meters per second unless it tells you otherwise. I just put that in there to give you a basis for looking at how fast that was. Okay, so that concludes this video on energy and power.